Hello, everybody. Welcome. Good morning. This is the Open Research Institute FPGA Meetup for Tuesday, November 5th. And what we do is we talk about what we've done over the past week or so and what we have planned over the next week, if we have any roadblocks and if we need any resources or help. And so I think we have some news to report. So Matthew, would you like to lead us off today?
Okay. I'm sorry I don't have a camera set up today, so I don't have no video. But anyways, I think the lab work that had been done while you guys were at the DOM conference was really helpful. I feel bad about all the energy expended, but we did find two bugs, coming out of that. So that was useful. And the one bug was kind of interesting in that it was a resolution error in terms of both number of phases that we use to describe the sinusoid, the F1, F2 NCOs, as well as the amplitude steps. So we're using 1024 phases, and we were using 1024 steps from minus 512 to plus 511. And so what was happening when we're running at the full NCO rate, there's some multiplies and between the F1 and F2 outputs, the sine and cosine outputs, and then adds and subtracts in order to generate a 2T clock, twice the bit clock rate. And one of the clocks was getting a double edge occasionally, and that double edge caused the PRBS monitor to shift prematurely. So every time we would get this double edge, the PRBS monitor would shift, and then our bit rate, error rate would go to 50% at that moment. And the reason that this was happening is the resolution, that 10-bit resolution in both phase and frequency, just caused some values to repeat. So out of the NCO, so that, or at least not necessarily repeat, but they ended up matching between the cosine and the sine from the F1 and F2 over multiple sample clocks, but they would not match for one of those clocks. And that created the double edge. It's, you have to look closely at the math and the samples that were coming out. But we reasoned it as a resolution issue, so we could either go more than 10 bits, or we're significantly oversampling for the NCOs. They're running at 61.44 megahertz, but in this particular simulation and efforts in the labs, the F1 and F2 are like 400 and something kilohertz. So they're significantly oversampled. So I added a sample discard circuit to the NCOs that brings the effective sample rate down to about 2.5 megahertz, give or take. And so that will also effectively reduce the resolution issue, because we're moving faster, right? There's less samples, and so the samples are further apart, so we don't get those repeated values out of the NCOs that match between the F1 and F2. So that resolved the double edge issue. We saw that was resolved in simulation, so that was good. And then there was also an error in how I implemented the sample discard circuit. And this manifested after we changed the F1, F2. So that was the other big thing we found while you guys were in Canada, was the F1, F2 were not the right values, so we weren't generating a true MSK waveform. So that I corrected that, but missed this issue with the sample discard. So that was identified, and we fixed that. And I'd say Paul was really helpful in this, is that I had uploaded the waveforms from the simulations, and he installed the GTK wave viewer, and he dug in and was asking me questions, and that was really helpful to see stuff I had missed. So thank you, Paul. So I think with that, with those two bugs, I'm cleared up. I've run a almost 8 second simulation um, for the design, and had 0 bit errors about 2 milliseconds into the simulation through the nearly 8 seconds. So I was pretty confident that even though, previous simulations I was running for 100 milliseconds or less, things could happen after that, even though it looked good. So running a much longer simulation gets us in the same time frames as what I think we're doing our trials in the lab. And so giving confidence that the loops weren't wandering off sometime later. So I think that simulation has given some confidence. So I'm hopeful that we're seeing, that we will start to see good results in the lab that match the simulation. So I think that's the news I have on the modem front from the simulation and RTL point of view. And then just looking forward, assuming that we're starting to get some good results in the lab, there's some improvements to be made to the design, adding a lock detector, adding some sort of, if we can derive an SNR estimate, I think that would be useful in a power detector, and then also moving, if we can, to a quadrature output. So those are things to be looked at. They're all, I have a number of things that I've put into the Trello board for us to come back to and pick up on once we have something working in the lab stable.
Yep. Thank you so much. That's an excellent summary. And we do have some very good news, it looks like, from the lab. We had a period of time where the simulated code, the simulations that Matthew's running, uh, gave zero error and looked like it was working, but we could not duplicate this in the lab. But as of this morning, it looks like we are. So the next bit of work, looking forward today, moving forward, is to go in and thoroughly prove that it's working. So I'd like to turn it over to Paul because he took the results and made some visualizations, some graphs. So I think he can show what we're now seeing in the lab. So turn the floor over to him.
What I've got is a graph of the last file I have, which is, well, let me show it to you. Okay, you should be seeing a data graph screen. Down in the lower right-hand corner is the graph. You can see all the other components. Um, this is basically one long run with cumulative bit counts and bit errors. And bit errors are in red. And you can see they're both growing approximately linearly. And that red is at about 5% of the black. And I don't know why. And I don't seem to have the file that has all the successes that you mentioned in the Slack with tags of 3. I do not have that file at all.
Yeah, it's still running.
Okay.
I posted a screenshot of the first maybe dozen results in Slack, and it's interesting. So it looks very promising. It looks like we are getting very, very similar, if not the same results as the simulation.
You can see here that the zero error rate is consistent among all the 3 tag lines that have come out. This shows the search in gain space. I would like to graph more details on that to see what's going on.
Yeah,
One thing,
you should have it in your the big uh directory. So I did a run of search space with the entire results and sent it to you, but we'll figure it out later and we can graft it into this meeting as a
I'm pretty
report.
sure the one I showed you with the single rising edge and no
Yeah, that should be
at
frozen at
all.
the recommended gains that are in the simulation, which is decimal 200 and I think 256 and then zero. The the final column on the right there is the gain pair. So the left hand 16 bits of that 32-bit register are the proportional gain. So in this particular screenshot, you can see that it's searching through. It starts at 1 and goes up to 13 hex, but the integral gain is we held it at 0. So that's kind of the experiment that we're doing right now is to search over all the proportional gains in the loop.
And one comment here is initially I thought, well, the accumulators are kind of really, they're accumulating, but they're not participating in the loop because of the zero gain. But what is interesting about the accumulation is that it is trending downward as you're increasing the P gain. So that might be that might be a useful indication because it's just saying that we're accumulating less error as the P gain is increasing.
Yeah,
Um,
that
I'm not
does
sure
make
that
sense.
yeah, I'm not sure that speaks to loop stability or not, but it is but if nothing else, it's a good indication. I mean, if as the proportional gains up goes up, we're going to react to errors faster. So presumably, the error accumulation would be less. At some point, I suppose, we'll see this reverse because the P gains get too large. That would be interesting.
Yeah. Yeah, I'm looking forward to doing the whole search space. So I think we'll probably do a presentation, a video recording just of that result when we get it. We might be able to do that later today. So just in short, the we're now getting zero errors with both. Well, we got zero error in digital loopback. We switched to the RF loopback. So the Pluto is actually in a radio frequency loopback. This is actually going out the antenna and then looped back to the receiving antenna. And we did that in order to kind of make it more real, more realistic, and also kind of force it to use the radio instead of just the internal FPGA paths. The next step is to start to add like adding attenuation to this path, and also adding in the error. You can add in errors in the PRBS, things like that, in order to kind of force it to behave in a more realistic manner. So we should have those results very soon.
I wanted to
Um,
show, I
uh,
wanted to show this graph too. This is something else we have reminded ourselves of recently. This shows zero error on all but the first two trials. And the first trial, uh, I think, is doomed to always fail because we start uh, initializing the PRBS monitor while the beta error rate is still too high and therefore lock on to a nonsense sequence. And then the second error one is failing because we try it with inverted data. And then after that, that's zero because everything is right on a perfect digital loopback. So I think we're gonna have to account for that in our test scenarios from now on if we want to get meaningful numerical results.
Okay. Yeah, we think we can do that.
so one thing to note just with the RF loopback or the RF over the air, I'm just curious, or we might want to keep in mind that if there's any other stray over the air signals, in the air, um, if they're if they're above 1.25 megahertz, they could get aliased down into our signal space, since we're doing a sample discard rather than a decimation filter. So that might just be something to keep in mind as we're doing the RF. But I'm hoping we get good results there.
Well, yeah, that test that Paul showed with the three tags, and so the data is tagged from the test code. The tag of one means that we're just still trying to figure out the receiver, the 180-degree phase shift. And I think that's something that you have added to Trello already, is to put in a differential encoder, differential decoder, so that we never have to worry about the 180-degree phase shift test again. I know that that's been on the list for a while, and I think it's in Trello. So that'll resolve this uncertainty. But as of today, what we do is the first sort of battle is to figure out whether or not to figure out the 180-degree phase shift, and that's the RX invert. So what we do in the first loop is just bang, bang, back and forth with the RX invert, and then we look for whenever the error falls. So you can see like those first two trials that Paul showed, that's what's happening, is that we eventually beat it down and get through that problem. And then we go into a second loop, which is, hey, do we have low error rate? Is it below 0.1% error in for the loopback? And then after enough of those have happened, we declare a success and then we increment the PI gain to go search for another working PI gain. So that's what the tags come from, is that if you can fall all the way through to 3, that's like, hey, it's working, it locked it, it maintained it. It wasn't just a temporary, like we hit 0 once. It actually stayed there for a fairly significant number of bits. So
Yeah.
that's kind of how that's the
Hey,
lay
Ray.
of the land on the test code. So yeah, we should have a lot more to talk about really soon. But I think that I was cautiously optimistic when what the thing that really kind of clinched it was last night. Matthew had introduced this new register, so we moved these sample discards to a new register. They were originally, I think, in the MSK control, so we discard some receiver samples in order to kind of lower the data rate essentially. So we're lowering our rate by discarding samples, and that, and then it was like, okay, well, we also need to do this for the NCO, so why not move both of those to a new register? And since it's only 16 bits, um, it was a 16-bit register. And I know that probably a better C coder would be able to figure out how to handle a 16-bit register in a 32-bit register world. But what was happening is this new 16-bit register didn't get to the hardware for some reason. And so we had asked, okay, well, can we make all the registers 32-bit? Just make them 32-bit so it's systematic. And then I did not expect this to work. I was expecting to take the new firmware, run it, and have the same problem again, that we had 50% error in the lab and a really nice looking simulation. So the simulations over the past couple of days from Matthew's lab have been great. It looks like it's working. Um, and when it popped up with 0 error, I didn't believe it. And so we'll continue to try to make absolutely sure this is not some sort of weird fluke, but it looks good. It looks like we're getting the results we expect.
And
So
it's very cool. And
yeah,
you could also
it's
do
good news.
bit error insertions just to see as
Yes.
well that the things are doing what they're supposed to. Yeah.
Yeah, you did that yourself in the simulation because some of the visualizations and when you show the simulations working, you're like, okay, and I also inserted an error to make sure that it isn't like a fake. We're not getting a fake result of 0 error, which is smart. So
Yeah, and the
yes,
other benefit was that in the long simulation run, I was wanting to print as few things as possible so that I wasn't, slowing the simulation down, putting out stuff. So every millisecond, I think it popped out that little blurb that I sent, which was the number of bits sent and the errors and so by having inserted that one error at the beginning, if a block of I had the auto sync on, so it says set to 50 bits. So if there were 50 errors, it would resync. So if say there was a burst of 50 errors between my two 1 millisecond pulses or reporting intervals, then that one would have gone to 0. Um, and I would have known that something had happened. Or if there was just some number of random bit errors less than 50, then that number would have incremented. So it was another way to confirm that no errors were being taken with the auto sync enabled as I had it.
very good. Yeah, I think we'll use the same mechanism. So we do have the code that Matthew's written allows you to insert errors in the PRBS pseudo-random bit sequence or binary sequence. And then what we'll also do is add impediments in the RF loopback. So we'll do both, and we'll make it difficult for the signal and see the result, and then summarize all of that. If not before next week, then definitely by next week. So I think this is really good news. So again, cautiously optimistic about it, just out of habit. Uh, but I think that we've cleared enough roadblocks to where we can start getting good results over the air and then moving towards, okay, so there's a list of things, which Matthew's already summarized, and Paul's brought up a few of things to optimize. Um, and also another a big deal here is that now Aaron has a code base that he can use that we think actually does work, and the loops are working. And we may refine the gain recommendation, which currently is 256 for the proportional gain and 0 for the integral gain, but we may be able to give you more more better numbers with the searching. So the test code that we have in the lab is designed in order to do an exhaustive search of the search space for PI gains. But as of today, that gain seems to work. And anyway, I'd like to hand it over to Aaron to give us any update. And now that the current build in GitHub looks like it's functional, um, maybe like where you plan on going next with OpenCPI.
Sure. Yeah, that's really good news that it looks like we got everything working. I'm excited to plug it into what I have in my code base and see what results I get. In OpenCPI implementation, we're using the different PBRS, which can validate even more further that everything is working. What I've done in the past couple of weeks, I've been working on the Spectrum viewer. I've been able to, I'll share my screen to better describe it. But so last time I presented this, this was the implementation that had basically the Pluto SDR and sending the FFT bins over MQTT and then plotting it out on another computer. But I've been able to get in OpenCPI, consolidate that where everything's running on the Pluto SDR. The blue boxes are what's running on the FPGA, and the green is what's running on the ARM on the FPGA. So all you have to do now is just pull up the browser to a specific port, and it'll bring up the same view that I showed a couple of weeks ago. Along with that, I've been cleaning up the repository where this is stored and started to include some documentation. And one of the features of OpenCPI is that each of these components can have, and the applications can have their own documentation, and we utilize Sphinx. So this is what I have so far for the project that hosts some of the components described here, as well as the two applications. I did decide to have both implementations, the MQTT version still, as well as the WebSockets, which is the standalone application that runs everything on the Pluto SDR itself. The next thing I'll be working on, which I've already almost have in a working state, but get the continuous integration, continuous deployment that builds these things. I had that working with the Opulent Voice and the MSK, chunking out basically artifacts and binaries that execute on the Pluto SDR using OpenCPI, so for the end user to get up and running. So I plan on doing the same here. I have the repository set up, and I have several scripts that go down the build process in Docker containers. So it's an automated process. So that's what I'll be working. But now that we have had some success with the MSK, I'm definitely going to go back and start working on getting that implemented in OpenCPI as well.
Fantastic. Thank you so much for the update. And of course, please just let us know if you hit any snags, see anything strange, have any trouble whatsoever. We'll continue to give reports and to work towards optimizing the design and hopefully without breaking anything, but we'll give you a big heads up if there's a branch that's wonky or anything like that. There's lots to optimize in this design, but it's pretty darn good. So we're very happy about this. It's always good to have your implementation in the lab match the simulation. That's I have to say a great feeling. Okay, Paul, anything else? Anything I missed?
Not that I know of.
Okay. Yeah, what I'll do is I'll make some files from the test code from the PI gain search test code, and then you should have plenty to graph with data graph. And then we'll do the things that we discussed in this meeting, add an attenuation to the RF loopback and also going in and deliberately adding errors at different rates in order to see the result and publish all of that. And we got some questions through our website about whether or not we have a version of Opulent Voice that does MSK targeted for things like general purpose processors. So we're starting to get questions about that. And just give a little background on this question. The original version of Opulent Voice was 4-area FSK, and this is what everybody uses for the digital voice modes, VHF, UHF, especially amateur public service, uh, lots of Motorola and DMR radios. They all use 4-area FSK. And it's 4-area FSK, and it's sort of like supposed to be continuous phase, but when you look at the modulation index, not quite. Um, and yes, we do have a version of Opulent Voice that's 4-area FSK, and this is what flew on the University of Puerto Rico's sounding rocket. Works great. Uh, but changing the modulation to minimum shift keying, the effort has been on the Pluto mainly, targeting the Pluto, but an implementation for FPGA and ASIC. And we talked about having a general purpose processor implementation. So I kind of like to open the floor for comments on that, where that effort is, whether we think we should do it in parallel or after a little more effort on the Pluto FPGA version. So I don't, Paul, if since you are most responsible for getting the Raspberry Pi version of Opulent Voice working and working with the University of Puerto Rico, if you have any opinions on that.
Well, I'd be inclined to say that it would be a little too soon to start that now. Once we have everything well understood in the existing implementation, then transporting it over to processor-based implementation ought to be easier. I don't know at what bit rate we'll be able to actually support it in the general processor, but it'd be interesting to find out.
Yeah, I think that was our first concern, and moving over to FPGA was what we wanted to do. That's what we want to do in general at ORI because most of our work is FPGA targeted. A lot of it's on general purpose processors, but there's this big three-legged stool out there. You have GPUs, graphical processing units, and all sorts of interesting GPU stuff available to you. You have FPGAs and ASICs, and you have general purpose processors, and all of them advance and get faster and faster. So it's kind of your choice as to which leg of the three-legged stool to go with. So we're a little bit FPGA biased, but having the implementation for Opulent Voice, the 4-area implementation, it was only ever available on a general purpose processor. We did not attempt to do 4-area FSK on FPGA because MSK we believe is a big step forward. So yeah, I think it is probably too early, but we may want to consider doing that down the line if it could possibly work. I think that the bit rates are too high.
Well, I have a couple comments here.
Oh, please go ahead.
Yeah, the one, you know, one of the things, we wrote this in VHDL, wasn't absolutely necessary. My career has been VHDL, so it was my go-to when we started this. But we may want to think about moving it or porting it to like System Verilog, and there's a couple reasons. One is there's much better tooling for Verilog. Open source tooling for Verilog is much better, and the RDL compilers for Verilog I think are better than the one we're using. So there's a couple of reasons to do it. And then there's some Verilog simulators that are really fast. One is called Verilator, and it actually would take the code and generate a system C model or a C model, and then we could run that and see what rate we get through it, right? So we could have potentially even a common source code. It's a little bit simplistic in that things are implemented in the general purpose processor. The processing structures are generally quite a bit different, but you could prove if the simulation could run the full bit rate, for instance, then certainly the general purpose processor could. But it might just be interesting if we were to go that rate. I'm not suggesting at this moment that we do. It's just something I keep in the back of my mind, and I did put a Trello item in for it.
I concur. There are some advantages, clear advantages to Verilog and System Verilog and all of that. And yeah, that would be pretty exciting to see if we could we could get the sort of the C implementation from that, or at least it would give us a start, a code-based start. So yeah, let's keep it on a burner. I think the front burners are occupied. Yeah, and it's not really a back burner thing. More like, that center burner that you got on your stove. So I think we'll keep it in mind, and yeah, that would be a real nice thing to add to the repository, to add to the product. Okay, very good. Any other questions or comments? And of course, I see Rick's with us today, so I can open the floor to him in office hours. And so, any other comments or questions for all the things we talked about today before we close? All right, everybody, thank you so much. We're going to do a lot more work with this current firmware build for MSKA Pluto. And so please keep an eye out on Slack and published things on our YouTube channel. So that's where this will go. Some walkthroughs and some visualizations and so showing you what we got. But just to summarize, it looks like what we're getting in the lab is matching the working simulations, and it's been a lot of hard work from a team of people who are fantastic to work with. So big thank you all around, and really looking forward to the next week. Okay, everybody. So I'll stop the recording here and see you on Slack and next week, if not before. And now we'll go into office hours. Right.